Hey, you're at the new Goose channel. My name is Dmitry, and recently I've done HTTP web server in ARM assembly in under 200 lines of code. It's literally 200 lines of text in assembly, and it works as a pure HTTP endpoint. Let me show you how it works. So if we're going and sending the request to the HTTP to the mom, it says ask your daddy. If you're going to dad, it says what it says. And you can see that dad is gone. True, but real. And it's a real HTTP web server. So if I'm going to the real endpoint and saying like, your browser will be able to send the requests, and it's done in assembly in 200 lines of code. Even if you'll do something like post request, let me show you, here is the post request. It will say the method is not loaded. So it has a real routing, it has a real validation for HTTP requests, it has a real login, and behaves more or less like a real HTTP endpoint. I wouldn't say that it 100% spec compliant and it works just like any other HTTP endpoint, but for 200 lines of code, I think it's pretty impressive even for myself. So let me show you how it works. And even if you have never been working with assembly and you have never been writing it, 200 lines of code is something that is really easy to wrap in the head, especially, I hope my explanation will be helpful. So let me try to explain it. So assembly is always a text format where the first thing you define your constants and URLs, and then you go with your instructions. So here is basically all of my responses: the mom response, the length, the dad response, the length, and the default response, which works both as 404 because I don't have space for 404, and also for method not allowed validation. There is requests that we matching for, and also some login messages, which you can see at the bottom, which we say the connection closed. If we start the server, you can see that it logs which port it's running on, which is pretty impressive for 200 lines of code. I'll show you why. The server is listening and so on and so forth. Then you have some global variables. That's not a big deal, we'll touch it later. Then we have the text section, which defines some required attributes and some basically constants which are used, not text context, but the actual numbers context. Okay, here you can see the print function. Yes, assembly doesn't technically have functions. It's actually a label where CPU will jump into, execute all of this instruction, and then return back to the caller. But technically it works like a function, so it's a function. And all assembly calls are always expect some registers to be set to specific values. It's just kind of a convention. So here for this function, I expect the x0 to contain the message pointer, the address to the string we want to print, and x1 would accept the message length. And then we call the syscall. This is always in macOS assembly, the SVC 0x80 is always a syscall, which takes the number of syscalls from the x16. So now we do the for syscall, which is right. And this syscall expects x0 to be a file descriptor, which is in this case stdout. Or it could be a file, or it could be a socket to where we will write something. This is important part. The x1 to set to message address, and x1 to set to the message length. So we basically swap the register and call the endpoint, and it just works as a print function. Nothing really complicated and scary. So now you understand how the print function behaves. Let's now dive into the actual execution of the assembly world, how it starts when the binary executables start working. So here is our entry point, and here you can see that we do two preparation steps. They're purely optional. They're just making life more comfortable. So here I do the log of the original thing. Let me run the assembly for you one more time. So here I do this log, and here I do the transform for HTTP port constant into the byte host network order, which both use the libc function calls.
Are you sure this is legal?
I don't know. It's fun though, isn't it?
Which is standard function of any C libraries, and it's used everywhere. But wait, is it a cheat-in? I said it's 200 lines of code, but it's a literally, I'm using a dependency, kind of, but it is not really true. So in fact, I use everything I use to build the library. You can see here, I use the system SDK. So your SDK, macOS SDK, is already including libc by default. So I don't need to install anything, and there is actually no additional code is used for this specific assembly. I just use what system already provides me by default. But basically, these are totally optional things. I just did it because I can, because I could. So let me wrap it up. So in order to do the printf function call, you need to firstly prepare some values on a stack. So firstly, we allocate some value on a stack by basically reducing the stack pointer by 16 bytes, which is required for macOS because macOS stack pointers are aligned always by 16. Now we load our HTTP port into the register, put this register on a stack pointer, then load the start message, which is a string. You can see it here, which is basically a C-like printf string. It is a C printf string template. And then we call the printf, which automatically reads both the message, the format message, and the first value on a stack, which is our HTTP port. And because it knows that it should be a number, it reads the number and prints something. And then we return stack back to the normal value. So you can see, yeah, and now you can also see that we also load the HTTP port. So they both are just a way of working with this specific HTTP port constant, because the network order, so networking thing is always expect the values to be in a specific network requested byte order. So basically first two bytes are swapped. So we need to swap them. And in order to not write it myself, because it's a little bit annoying, I also use the libc function instead of doing a weird like hex value that is unreadable, and to not define ports two times in different places, and to have an ability to change the port on the flight. Like here you can do something like 7070, then I'm going to this thing, rerunning the whole assembly, and you can see that 7070 now works. Now I can go here and say, let's go mom, and it say the connection is failed. So now I need to go to the 7070, and now you can see that our HTTP point, now HTTP endpoint now works, which is very comfortable to work with. So we just do, again, we do the same, literally same thing. We load the thing we need to write it on. So we do the socket address, we load into the memory. So we can do something even like that. So we can do something like that. It will be probably more understandable. We first load the first register, which is 0 register. It's now the int view of the 0 of the first register. We call the function, and now v0 will contain result of this function. So it's now swapped byte result. Now we'll load the socket address, which is our global variable, which is defined in, let me just do something like that. So which is defined in the data section, which is mutable basically, and we store the result of this function into the socket address struct. So now the socket address struct contains the variable. So in C, it will look something like that. Let me show you. So it will have the struct socket address. It will be one value, which is port, which will be UN16T port. And then you have, let's do this one. And then in the main thing, you do something like int UN16T value equals tons of 6969. And then you do something like socket address, but instead of doing this, we firstly initialize it with the port equals 0, and now, okay, it doesn't matter. So, and now we do something like address port value. That's it. That's what happens in here. So we firstly call the function and put the result on a socket address struct, nothing more. And it's even like, I don't know, it's 3 lines of code, and it's a little bit more lines of code in assembly. Okay, no problem, but it's pretty relatable. So now we enter the actual networking code, and it's fairly simple. Everything, all of the TCP stuff that goes under the hood of HTTP happens on a system. We don't write any transportation code and actually anything. So all we need to do is to do something like that. Basically, it's just an order of syscalls that we need to do. We need to create socket, we need to bind socket, we need to listen on the socket, accept the connection, and now when the connection is established, we can do something read writes and then close the connection. And that's it. And now what we will do is basically do all of the things. We just prepare some data. We put x0, required thing that I just found on the internet that I need to do. We create the socket stream, and we create the socket create socket syscalls, which is 97. Boom, that's done. Now we're checking for error, and if there is an error, we print an error and exit in the application. Okay, that's it. So here again, we need to bind the socket. No, it is not the binding the socket. It's just required thing to make system give us this URL. So the systems are the system sockets are not free URLs automatically when you exit the application. So we need, if we want to quickly run the application, we can just ask system to give us this address again, and it will give us it back if it's not actively listened by the other process. So it's just a convenience function that helps to rerun the application quickly, but it's also not that important. Okay, great. So now we need to bind the socket to the specific address. And notice that we use the same variable where we just put the port into. We just use it the same way, and we just passing it to the new syscall. So now we retrieve back the x19, which is now holds the result of the create socket. We return it back to the x0 to pass it to a new syscall, load the socket address into the x1, pass in some constant x into x2, and call in the syscall number 104. Same thing, checking for error, boom, we created a syscall. Now we need to listen on it, same thing. Load the variable from x19, which is an original socket, because right now x0 will contain the result of the previous syscall. So we need to save to one variable and then load it back to the x0 to create another syscall, right? Same thing, preparing some data, calling the syscall, checking for error, nothing else. And now we use our print function to print some log message. So you can see that this is our print function, which is literally just few instructions. So we load the listen message, which is defined in the constant section, right? And the message length, and calling the print function. And this is the log message you see right here. So, okay, so we're now all settled with all the preparation. We have our socket done, all of the logs done, and we're now ready to enter the request loop. So to accept the connection and to write actual response. So you can see here is a request loop label. It's a label. We just be passing it. So it's just a way to return back to it. So we're just going down. And now we're again preparing some data. So we put an x19 into x0, preparing some data, and running the accept syscall. This syscall will actually wait for any other calls. So now we're in this state. So yeah, if I will rerun it, you will see that we're now in this state, and we're just waiting for a syscall. The thread is on hold, basically. And once we do accept the syscall, we're checking for an error. And if there is an error, we return back to the request loop. Come on, it's 200 lines of code. There is no actual error messages and logs and other stuff, but it's not that big of a deal, to be honest. So if we have successfully received a connection, we save the result of the client socket to x20, which is now in x20. For later, because we need to somehow manipulate it later on. And now we need to read from the socket. So you can see if I will run this request, you will see that this is a request. HTTP is just a convention of how you send the data, and all the data is basically a string. So if I will go here and will run the request from the browser, you will see that from sends the whole bunch of different headers from for whatever reason it does it, and we can read it from our assembly code as well. So we need to somehow read it. In order to do this, we need to allocate some bytes on a stack. It's not the correct way, so if your request will be larger than kilobyte, it will fail. It will not crash, but it will be bad. So, but it's, come on, I'm not running this in production. It's just a matter of fun, right? Or education. So we just allocated some space on a stack, and now we put the x20 into x0. I did this just to make it clear that this is a request socket. Now x0 anyway have this x20 in the Yeah, x0 contains the same value as x20, so we can just delete it, but it's okay. It just to make it more clear that this is client socket. So x1 would contain the message that we need to read in, and this message is just so x1 will contain the stack pointer, which is a pointer to buffer where which will be filled with the actual request. The x2 will be a size of a buffer, which is 1024. Now, when we call the read syscall, we can print the request, which is what happens when we lock the request. But here's an important part: the buffer address here would be set to the stack pointer, but the x1 will be filled with x0, which is the result of the read syscall, which is the size of the read buffer, which you can actually see in the read function in C, which is literally same thing, right? So you can see the read function in C receives the file descriptor, which is the client socket, the buffer, which is now a stack pointer. The size of bytes is the bytes, yes, so this is the function, and the size of the byte, which we filled with 1024. And it will return back the result, the read result length, which is now in x0, which we now can pass to the print function to print the request and to not have issues with wrong memory access because something is not filled yet, or some weird characters everywhere, which is kind of neat.
Nice.
Okay, great. So now we have accepted the connection. So now it's time to do the route-in. And the route-in is probably the most complicated part here, but you can see that's it, basically. It's just like 13 lines of code. So it's very easy. We just get in the request from the stack pointer. We load in the mom URL into the x1 and call in the str function from libc, which matches the string. And this is actually a really complicated part, but I insist that this is coming from my system. I'm not installing this code, so it's still 200 lines of code in assembly. Okay, so now we have this mom URL, and noted that mom URL and dad URL always contain this get stuff. So if I'm going here and sending the request, you can see here that it's a post. Let's remove the post stuff. So we'll just remove the post stuff, and you can see here that HTTP endpoint will always contain this kind of string, right? So we can match on the whole HTTP 1.1 stuff but we don't support any version of HTTP actually, so it's totally okay. So we just load this specific pattern into the x1, calling the string, and if the result of string contains 0, which means that there is successful match, we go and load mom response. If it's not, we just do same thing. Okay, it's not really correct layout. So we go in and check in for the URL, that URL. Doing same thing, load the dat URL match, call in str, and then if it's matched, we'll load the dat response, otherwise load default response. And the load response is just the identical lines of code, which just fills with a different constant, either mom, dad, or default response, which loads the address into the x21 of the message we need to send. x22 will contain the message length, and then we call the send response in all three cases.
It's about sending a message.
And now the most interesting part. We need to write the actual response back to the client socket and close the connection so a user can read it and understand that something happened and there is some response back. Okay, so how it happens? So first of all, we'll load x20, which contains the socket, the client socket pointer. What does it mean? It means that all of this time, x20 had some specific value, which was just on a CPU in a specific register, and we just move it into the x0. So the next syscall understands where to, it knows to read from x0, so we just fill it in to the x0. x21 contains the pointer from this function, x22 contains the length, and now please make sure we are running the same syscall as we did for the print function. It's literally same syscall, it's same write syscall, which in case of print had x0 filled to 1, which is standard out convention, and now we are writing into the socket to the client socket and nothing else. So we, instead of writing into stdout, we did the same little thing, and the system did the same thing. It just wrote into the client descriptor, and basically that's it. This is the Linux way, and I think it's very interesting. So basically, as you can see, I don't do anything. I just call a bunch of system API, system calls, and that's it, right? So now we do another syscall, which is closing the socket, which x20 now still contains the socket descriptor. We need to refill it to x0 because the syscall could overwrite the result, and it actually did, I think. We probably need to check here for error, but I don't know. It doesn't really matter right now. Okay, so here we do close the syscall and print in the connection closed message. That's it. Literally, that's it. And then basically we return back the stack pointer to 1024 because remember we allocated the 1024 bytes. We don't need them anymore. We already read all of the information from the stack pointer, and then we enter a new request loop. So we're waiting for a new connection. And that's it. That's it. This is the actual HTTP web server implementation that works. It has some logic inside. It even has some lore inside, and it's literally 198 lines of text. And basically that's it. That's it. You don't need anything else to work with HTTP servers. They are fairly easy, and most of the functionality happens on the system side. You just need to call the different system functions in a specific order, and add a little bit of your own logic on the data you read from the socket, and write something to the socket back and close it. That's basically it. Thank you for watching. It was NeoGoods. If you like some kind of assembly code, if you really like my breakdowns, please let me know. You know how. You know how. GitHub sponsorship. Yeah, it would be great. It would be great. Thanks. Bye.